it is time for our first exercise. Generally, when it comes to exercises, I do advise that after the exercise question has been posed, you pause the video and try to solve the problem for yourself, and only refer to the remaining part of the video with the solution once you have either solved the problem or you need help getting further. So for the first exercise, let us compute the basis vector in polar coordinates, both the tangent and the dual basis. And to remind ourselves, the polar coordinates in the Euclidean plane are given by x equal to rho cosine phi and y equal to rho sine phi. I now recommend then that you pause the video. So let's first compute the tangent vectors. The tangent vector E rho is by definition given by the partial derivative of the position vector with respect to the polar coordinate rho. Since the Cartesian basis vectors are constant, this is given by dx d rho multiplied by E1 plus dy d rho multiplied by E2. Computing these partial derivatives, we end up with E1 cosine phi plus E2 sine phi. Doing the same for E phi, which is then equal to dx d phi E1 plus dy d phi E2, we compute the partial derivatives and find rho times minus sine phi E1 plus cosine phi E2. When it comes to computing the dual basis, we will do it in a slightly different way. We start by computing the gradient of the Cartesian coordinate function x. Inserting the definition of x in terms of the polar coordinates, this is equal to the gradient of rho times cos phi. By applying the product rule for derivatives, this is equal to rho times the gradient of cosine phi plus cosine phi times the gradient of rho, which in turn is equal to minus rho sine phi times the gradient of phi plus cosine phi times the gradient of rho. We can now use that the gradient of phi and rho are by definition the dual basis vectors in polar coordinates. So we have that this is equal to cosine phi times E rho minus rho sine phi times E phi. But the gradient of the Cartesian coordinate x is also equal to the Cartesian basis vector E1. So what we have just done is to re-express the Cartesian basis vector E1 in terms of the dual basis in polar coordinates. We can do the same for E2, which is equal to the gradient of y, and we find that this is the gradient of rho sine phi, which is equal to sine phi times the gradient of rho plus rho cosine phi times the gradient of phi. Or in terms of the dual basis vectors, sine phi E rho plus rho cosine phi E phi. This is now a linear system of equations that we can solve for E rho and E phi in terms of E1 and E2. We find that E rho is cosine phi E1 plus sine phi E2, and that E phi is equal to 1 over rho times minus sine phi E1 plus cosine phi E2. We mark the result of this exercise, which is the expressions for the tangent basis vectors E subindex rho and E subindex phi, and the dual basis vectors E superindex rho and E superindex phi. We can show this result graphically if we introduce our origin O, then the E rho vector field is always pointing away from that origin, and it always has a magnitude of 1. In contrast, the tangent vector field E phi is always orthogonal to a line from the origin, and its length is variable and proportional to the distance from the origin.